So I don't know how many have heard about Euclid before. Can you please raise your hand if you have ever? Oh my God, I was expecting more. This is going to be interesting. So the Euclid spacecraft is actually this spacecraft that you see here. It's a mission of the European Space Agency that actually was adopted a long time ago, more than a decade ago, but we launched really recently. And as many of you haven't heard about Euclid, we are going to start with something that dives a lot my imagination. So we're going to start for the Euclid, what we made at ESA, which is a trailer that we prepared before the launch, which actually is really, really, really exciting. So please, just keep listening and watch.
In 1915, Albert Einstein astonished the world with his general theory of relativity. It described the behaviour of the entire universe based on the matter and energy contained within it. The theory sparked the modern discipline of cosmology and the hope that we would finally understand how the universe came to be. But in recent times, the effort to define what the universe is made of has given us a very big surprise. Visible stars and galaxies make up less than 5% of the universe's total matter and energy. Beneath this visible layer is a mysterious celestial realm, consisting of shadowy particles and unknown energy fields. For decades, astronomers have puzzled at their nature, calling these elusive substances dark matter and dark energy. ESA's Euclid mission will go in search of the answer to the fundamental question: what is the universe made of? A European-designed mission, Euclid is built and operated by ESA with contributions from the International Euclid Consortium and NASA. ESA selected Thales Alenia Space to lead on building Euclid, with Airbus Defence and Space providing the telescope and payload module. The telescope and scientific instruments form the heart of the mission. Together, they will observe billions of galaxies over more than 1/3 of the sky. Producing record quantities of data, Euclid will enable scientists to draw a precise map of the universe across space and time. This will allow researchers to investigate the effects of dark matter and dark energy on the apparent shape of galaxies and on their motion and distribution over immense distances. In turn, this will help reveal the true nature of dark matter and dark energy. The spacecraft and data communications will be controlled through ESA's European Space Operations Centre in Darmstadt. To cope with the vast amounts of data Euclid will acquire, ESA's S-track network of deep space antennas has been upgraded. These data will be analysed by the Euclid Consortium, a group of more than 2,000 scientists from more than 300 institutes across Europe, the US, Canada and Japan. Understanding the elusive nature of the universe has drawn astronomers throughout history. It remains one of the most challenging investigations in modern science, but Euclid is up to the task. The Euclid mission is a quest into the unknown, a mission to shine a light on the dark side of the universe.
Okay, so now let's go step by step. I've seen this trailer so many times and still I get, goosebumps every time that I watch it. Okay, so the trailer introduces us to one problem that we have these days in cosmology. So we cosmologists believe that we have found a model that is able to explain almost everything that we can actually observe in the universe. However, to make up this model, we have two main ingredients that we don't know what they are. And one is what we call dark matter. So dark matter is a type of matter, and we believe that is some kind of matter because it behaves in a similar way as the ordinary matter. So basically all the matter that things are made of. So not only stars, galaxies, planets, but even us. But it's a type of matter that doesn't interact with light. So we cannot actually see it directly. We can only infer how it behaves thanks to gravity. This is what the name is dark. But later, it was actually discovered, we already knew that our universe was expanding, but our universe is expanding faster than we expected. And we believe that there is some unknown ingredients, one unknown substance that we model that is responsible for this accelerated expansion. And we need at least 70% of this matter energy composition of the universe to be this dark ingredient responsible of the accelerated expansion. And we call it dark energy. I know that it's a little bit misleading that we call both ingredients dark. Remember, dark matter is because it doesn't interact with light, whereas dark energy, simply we name it dark because we don't know what it is. And even though it might be interesting that I state and I affirmed that we have one model that is able to explain, and we take for granted that this is the composition of the universe, we still want to know what is the fundamental nature of these ingredients so that we can actually understand better how our universe behaves, how it originated, and where it eventually will be. And based on these questions, there are fundamental questions on cosmology. Well, the Euclid mission is aimed to tackle them. So basically, this is what we believe, that is our universe timeline. It originated from a really big, dense, really hot moment, long time ago. It happened really long time ago, and it started to expand. And well, the first atoms, well, the first nuclei were created, and then the first atoms, and then the first stars, the first galaxies, up to the point that we are actually now, where we see some structure that we denominate the large scale structure of our universe. So basically how galaxies are located in our universe when we look at really big distances. And this is what we basically aim to do with Euclid. So with Euclid, what we want is to basically take pictures of all these galaxies, see their shapes and where they are located in the universe, so that we could potentially infer the properties of the expansion of the universe along time by means of how they look like. Because distances are so big in our universe, and the maximum speed of things that can actually move is the speed of light. Looking at really big distances means that we are looking in the past. So this is what we aim to do with Euclid. We aim to actually look at galaxies that are far from us, so we can actually trace the time history of our universe. And if you wonder how I ended up working for Euclid, well, basically it's because during my PhD, I have some intrinsic interest on understanding how the universe began. So we know that really right after the Big Bang, the universe had to go a really fast expansion. It grew exponentially in a really short period of time. This is something that we call the inflationary theory. This is the inflation moment of our universe. And this model is really nice because it's not only able to explain, it's part of our model to explain the observations that we see, but also aims to create a mechanism for the origin of these seeds in the universe. So basically, we know that galaxies are formed in our universe. We are able to see them, but that means that they had to be in the past. Some areas in our universe that were slightly more dense, so gravity could actually start playing its role, so that galaxies could later be created, stars and later galaxies. So basically, by mapping the position and the shapes of the galaxies, we could also see something, we could say something about the origin of the universe. But let's come back to Euclid. As I said, we launched on the 1st of July, and actually I have to say, I didn't expect it to be launching on the 1st of July, because the first thing that I learned when I arrived at ESA is that a mission is never launched on the date that it is planned to be launched. But actually with Euclid we did. We launched from the US, from Cape Canaveral, to SpaceX in the 1st of July, and this is the moment.
4, 3, 2, 1.
I wasn't really crying at the moment.
Vehicles pitching downrange.
So we actually have some colleagues here working in Euclid that had the opportunity to see the launch live. from Florida. If you want to talk to them, please go during the break. But yeah, this is the moment of launch. It was a really successful launch. We also retrieved signal really nicely. So now, in principle, we are ready to do science, right? But well, there are some steps that need to happen first. So we launched Euclid. Euclid had to reach a point that we call Lagrangian 2. So that is a special point between the Earth and the Sun, where basically Euclid is located, is making some company to other space missions such as the James Webb or Gaia. It's getting a really popular and expensive neighborhood in our universe. So Euclid basically arrived L2 like 4 weeks later. And we are right now in this moment of the Euclid timeline. So once that Euclid arrives on L2, well, with whatever spacecraft mission of the European Space Agency or NASA, or whatever space agency, you actually need to test that everything works well. Okay, so you turn the spacecraft and you basically check that the instruments respond. And we actually did that, and it seems that everything was working so that we could move to a phase that we call the performance verification of the spacecraft, when we actually test if the instruments are ready to perform science. This is what we are at the moment, and we hope that in the near future we can start actually taking pictures of the universe. So as we said, as I said, and it was on in the trailer, so the plan is to make a survey. So Euclid is what we call like a survey mission. It has a goal. It's not like the James Webb, where you can actually point and see different observations that you might be interested in. Euclid was designed, created, and launched with a purpose. And that means that we are going to make a survey during 6 years, when we are going to take pictures of 1/3 of the sky. And then I got asked, why 1/3? Well, it's not that we are not ambitious. The thing is that in the middle of this map here, we have some luminous contamination, which is from our Milky Way. So we are mapping 1/3 of the universe because, well, most of the things that we could potentially take pictures of are contaminated. And as I said, we are interested in really far away galaxies. So galaxies that can tell us something about the temporal line of our universe. So the plan is, as I said, we take some pictures, then we basically locate where galaxies are, and then by means of taking several pictures and also understanding, measuring the distance to those galaxies, we could potentially see a temporal line of how the structure was created in the universe. And this is what we call a 3D map of our universe. And we are ambitious on this because we are going to create the biggest 3D map that it has ever been built for Euclid. So Euclid is, well, actually I have to say I have the opportunity to see Euclid back in February, and I was expecting it to be big, but I'm also 150 in the Netherlands, so for me everything is big. But I was expecting it to be bigger, but actually Euclid is really big. It weighs quite a lot, but actually not a lot. It had to go through so many different requirements. Actually, I've seen some people here from the ESA project, from the ESA Euclid project team, so they can tell you a bit more about the engineering. There was like a lot of discussion to get these requirements done. The telescope is 1.2 meter diameter. And okay, I was definitely smaller when I was standing close to Euclid, but I can say that it was beautiful. It was definitely beautiful. So this enterprise takes a lot of time, okay, and it takes a lot of energy. Euclid couldn't have been built, even though, well, Euclid is a European Space Agency mission that gave the contract to the main contractor, that is Thales Alenia Space. They needed to be involved, like so many different parties in this enterprise, otherwise they couldn't have been going through. So more than 300 institutions, 21 countries, 80 companies, 140 industry contracts, a lot of scientists involved, and of course, a lot of money. But even though you're seeing a lot of money here, I just would like to remark that the contribution of a European citizen to the European Space Agency per year is around 1 cinema ticket only. So now you can weigh yourself and you see if all the science that we're aiming to do actually costs a lot of money or not. So let's talk about these 3,500 people that are involved, and actually I'm going to be talking about the scientists that are involved in the mission. So in 2011, ESA gave the power of the data retrieval, but also the data analysis and the instruments that are on board, that I will talk a bit about it in a minute, to the Euclid Consortium. So the Euclid Consortium is an association of different scientists distributed among so many different European countries, 14 in particular, but also we have contributions from the US, Canada and Japan. We are more than 2,700 scientists, and as I said, we are responsible as well for the 2 instruments on board, because Euclid have to take pictures, but also have to measure the distance to galaxies. So this is why Euclid have 2 instruments on board. One is what we call the visible instruments. Those are cameras that basically will take pictures on the visible, in the visible range. There is another instrument that is NISP. Basically, NISP will be used, it will be observing galaxies in the near infrared. This is what the NI stands for. And the other 2 letters basically identify a spectrograph and a photometer, that it will be used to measure distances to galaxies. And here we are. So these are the first light of Euclid. This is a real image, this is not a simulation. So once that we corroborated that the instruments work well, this is the first picture, the first light that it was taken for the visible instrument. And yeah, so you can see here all these small squares correspond to one of these squares, and you can see the quality of the pictures. And you might see, okay, it's not that astonishing. There are like a lot of galaxies. There is like a lot of detailing here. We have like an image quality which is similar to Hubble. The thing is that we are going to be taking thousands of pictures of these. We need, and I'm going to use scientific notation because first I'm a scientist, but second, English is not my mother tongue, so I always get confused between millions and billions, whatever. We are going to take 10 to the 9 photos of galaxies. So we need at least 10 to the 9 galaxies to be in these pictures so that we can actually do science with them. And this is one of the instruments. The second instrument is this one. This is NISP. And oh my god, this looks amazing. Okay? So we have like a beautiful galaxy here, a lot of the stars. We will be interested mostly in the small points that are really far away galaxies. But with these 2 instruments, you can actually construct the 3D map in our universe. And also, for that, you will need to produce something that we call cosmological observables or astrophysical observables. But my colleague Henk will tell you more about it. So thank you so much. If you would like to follow us on social media, use these or have a look at these hashtags. My colleagues from communications are being really busy preparing all this fantastic material that I'm presenting to you today. And I'm gladly taking questions now. Thank you so much. Thank you very much.
Very inspiring talk.
Maybe it's just me. Okay, maybe there's this spot. This is a spot. Okay, questions for Guadalupe? Yeah, here in the back.
What is the reference? What has been done before? So Euclid is not the first instrument looking to the universe. I assume that Swan Digital Survey is the point of reference. Can you give it comparison? What to expect from Euclid?
Yeah, so I didn't want to make spoilers because I know that Henk is going to make a comparison with different surveys in his talk. But of course, I mean, we are pioneering in the ambition. And of course, we are pioneering of making the first large-scale structure map of the universe from space. Okay, so this is one of the first missions that will be looking at these 2 observables, so basically measuring distances to galaxies and then also looking at the shape of the galaxies from space, and it's also the bigger one. But of course, the science that we are aiming to do with Euclid is science that it has been developed for so many years now, with so many different experiments. So for the case of weak lensing, which is one of the probes that Henk is going to be talking about, of course there are like many different experiments, like for instance one really popular is KIDS. And of course in the spectral case, well, we have also some other competitors right now, DESI, but yeah, okay, the Sloan survey, many other different surveys, but we are going to be bigger, or this is the plan, that we do bigger. Oh, sorry.
Yeah, the first in front.
Yes, I have actually 2 questions. But the first one, NISP is a spectrometer, you say?
A photometer as well.
Photometer spectrometer, but you showed a picture. Does that mean that behind each pixel there's actually a spectrum?
Yes.
Okay.
Yeah. So that's the key with this one. This one. Yeah. So basically, the plan is that we obtain the spectra for all the different luminous sources that we have here. And we do it like with, yeah. I know, this is a lot of work. Yeah, but we are going to do it, yeah, with photometric data and spectral data, both of them. And this is crucial, otherwise we won't be able to actually beat the cosmological information that we were obtaining with other missions.
You started to talk about the dark matter and the dark energy. Okay, now you get a very beautiful and very big picture of how the universe actually is in the time backwards. So how does it help you telling more about the black matter, the dark matter, and the dark energy?
Yeah, so let me see if I can go back really quickly. Okay. Okay, so for dark energy, which is basically the ingredient that we believe that is responsible for this faster acceleration, we know that our universe is expanding faster because we could measure how the universe expands over a period of time. As we want to look to very far away galaxies, that means that we could potentially classify galaxies based on their distance. The ones that are a larger distance, it means that are more in the past. By tracking the position of the distance all over time, we can try to get an estimation of the acceleration of how the universe is expanding. We can compare that with different cosmological models in which this dark ingredient, dark energy, is modeled on different ways, either with a field, either modified gravity, and then we compare the theoretical predictions to the data that we are aiming to obtain. That is for dark matter. For dark energy. For the case of dark matter, it's a combination of both probes. So of course, dark matter will affect the shape of the galaxies. This is something that probably Hank will be talking about. So we know that the shape of the galaxies that we obtain are distorted because of the presence of gravitational matter around it. As we believe that dark matter is the largest responsible of matter in our universe, we could try to infer how much dark matter it is based on how the shape of the galaxies are distorted.
First question, Dor.
Thank you very much. There was some regions where you were showing what regions of the sky will actually be observed. I thought that was interesting. You had a general survey, yeah, this one. And then I saw the orange circles are for the deep field,
yeah.
So that's looking further away. I was wondering how far is that and why is it such only three tiny spots for that? And why is it not more distributed in other directions?
Yeah, it's a really good question. As I said, okay, so the goal of Euclid, why we want to aim big and think big, is because we want to achieve a lot of astronomical data. So that means that we want to make a general survey in which we map the possible region of the sky. So this is basically the main survey of Euclid, so these areas here. Now, of course, it would be a pity that we put a telescope in space and we don't aim to look farther or more like on farther distances. Of course, you cannot do that for the the duration of the project because, of course, it takes time. To obtain all these regions of the universe to be taken pictures of from takes 6 years. So imagine if you would like to go as deep as the cases of the deep field and you would like to map everything, you cannot. I mean, you could, but remember, 1 cinema ticket per year. This is where it is invested, okay? So the deep fields of survey, the deep field surveys of Euclid, there are regions of I don't know exactly why they are taking like these regions here, but maybe some of my colleagues will actually answer your question. But I know that it will be used for calibration purposes, but also for astronomical observations. Of course, at the end, this is data, and it's data that will be eventually public for everybody. So of course, we aim Euclid for one scientific purpose, but it can be used for many other things.
Thank you.
So next question here, and then the final question, and then we have to move on.
And then I take questions already.
Yeah.
Connecting to the question about dark matter and your answer, so will there also be sufficient resolution to obtain rotational curves of many galaxies? Or Yeah, many.
Maybe in the deep fields. For sure not in the broad survey, but the deep fields I actually don't know. I don't think so because the resolution is not good. But maybe any of my colleagues, they are like as cosmologists as I am, so they care only about the big statistical thing. So maybe we will see. No, like Euclid is not meant for this kind of studies. Yeah, so we will infer how much dark matter it is based on other, like on a general stuff, like how galaxies on average are located and are deformed in shape.
I was wondering what determines how far back in time we could see.
That is the sensitivity of the instruments, of course, and the fact as well that this is something that I haven't mentioned, so I will go really quickly on that. So we know that dark energy started, if we believe that dark energy actually exists, and we believe that it is the responsible of this accelerated expansion, we know that dark energy needed to start kicking in on a period, and I will talk in units of redshift, because I don't feel comfortable with other stuff, maybe it's just because I'm a cosmologist. But yeah, okay, so from now up to 2 billion years, so basically redshift from 0 up to redshift 1.6 something, is when we know that this accelerated expansion of the universe started to be more remarkable. So of course, as this is one of the goals of the Euclid mission, we want to understand the nature of dark energy. We are aiming to map galaxies that are suffering this accelerated expansion. So the instruments are actually thought to be working on this region of space-time. So basically up to redshift 2.5 for the big survey, so for the broad survey. I think it's redshift 6 for the deep survey, although I'm not sure, but yeah. So the idea is to obtain a look of how the universe looked like up to 2 billion years, more or less, which is a lot. I'm getting stressed, okay.
Wait, the second